in my whole career. So I'm going to talk about global solutions from various aspects for the MHD. Okay? So this joined with my student, Xinfeng Hu, who is going to Korean Institute this summer, this fall. So first, I'm going to, of course, show you the equations for MHD, and then show you the global weak solutions, and also look at the incompressible limit from two aspects here. First is zero Mach number limit, and another one is hydrodynamic limit from the Maxwell-Boltzmann equations, and then the last thing is about the zero, the MHD, but with zero magnetic diffusivity. So let's see what is the MHD. MHD, of course, is we know that it is about the fluid in electromagnetic field. It has, of course, many applications. So the equations here you have. First, of course, here I'm looking at the viscous MHD. So besides the first three, of course, the compressible Stokes equations, you have this equation for the magnetic field. So H here is a magnetic field. Okay. So magnetic field, of course, has this condition. This one, of course, this divergence H equal to 0 is not actually an extra equation, but you can get it from the initial data, because if you take the divergence from here, you get the time derivative of the divergence H is 0. So if the initial data has zero divergence, then this is automatically true. Okay. So this is, and then of course here the conductivity, of course, and this is the usual Stokes here viscosities. Okay. So the mu here is called the magnetic diffusivity. Okay. So this, I'll show you, this could be positive or could be 0. Okay, so let's see the difference. Okay. So this is the equation, the system, and then of course we look at the Maxwell equation. Let's see, we only have a magnetic field here. So where is we're talking about the electromagnetic field. Where is the electric field? The electric field comes from this reduction here. So this is a Maxwell equation, Maxwell system, right? And then the Ohm's law is the current density J. But then in MHD you can set this to 0. Okay? Then of course you have that. So electric field is here. So therefore electric field is, of course, is not in the system of equation, but you can write it in terms of this velocity and also magnetic field. So isentropic case, of course, is like this. Okay, this is the isentropic case, and incompressible case, of course, you have that divergence is the incompressibility here. And also, so now this is 0 magnetic, means the mu equal to 0. Okay, mu equal to 0. So of course, this is corresponds to a physical regime where you have the negligible magnetic resistance. Okay, so you have the compressible case is like that. So the low viscosity for the equation of H. Okay, in compressible case, same thing. Now this one actually, in this case, actually this case is is much harder than the case with mu equal to 0. It is a very interesting problem, and but unfortunately, so far there is still no global existence in literature. Okay, actually, so because of the vanishing of this one, and everything becomes harder. So I will show you later about this special case. And when we talk about this mu equal to 0, in fact, there is a related model, related system of PDE which is very similar to this. Okay, very similar to this one. So, for example, let me show you. This is called viscoelastic fluids. So, of course, here is the Navier-Stokes equations, right? And you have some coupling term here. But if you look at the last equation, which is about the deformation gradient, you don't have any dissipation either. So in this one, you don't have any like viscosity or anything else. So it's just like this one. Okay. But actually this one, I'm not going to talk about any results about this, but actually this one, although they are similar but something for some problem, okay, this one actually is better than the MHD, than this case. Okay, because you can prove a very good property for the deformation gradient F. But the corresponding property does not hold for H here. Okay? So in some sense, this one is harder than this viscoelastic fluids. Okay? And of course, related also this liquid crystal. So this of course corresponds to the case where you have the mu, positive mu. Okay? So mu positive and correspond to this case. Okay? But they have some similar structures there. Okay? So it depends on the problem. You could do one thing, then do the same thing to the other. But, not everything. For some of the things you can do. So let's see. Start with 1D MHD. Okay. So 1D MHD, of course, is like this. So many studies about this 1D MHD, and we also had with Guichang, we also had a global existence, but with kind of a real flow. That means you have this. If temperature is high, you have this pressure and internal energy goes this pattern with certain temperature. Okay, so with this, in this high temperature case, you can prove the global existence. Okay. So, but of course, you can, for the MHD, you can consider this case, right? So everything is all the coefficients, viscous coefficients, constant. All the coefficients constant. If you do this case, if you consider this case, then the existence of global smooth solution for the 1D problem is still open. Okay. However, the corresponding problem for the Navier-Stokes was, of course, solved in classic paper instead 1977. But for this one, it's still open. Okay. So this one, of course, shows that well, many people can probably think whenever you can do for Navier-Stokes, you can do MHD. But it is not true. Okay. So like this simple case, right? For this classic result, you cannot, I mean, at least so far it is open to extend this result to MHD for this case. Okay. Of course, the problem is you have the, because of the magnetic field, especially in this 1D case, the pressure becomes that. Okay, so the B is like H. So it's like this. And even for multi-dimensional case, you can also write the pressure is P plus this one. The B is H here. So with this case, with this called the flow pressure of this structure, things becomes complicated. So even this simple classical problem still open. Okay. So that means you really need efforts to extend everything from Navier-Stokes to MHD, especially for the compressor case. Okay. So now let me show you the weak solution in isentropic case. So this is isentropic case. Of course, here I'm talking about the nu here is positive. Okay, nu here is positive. So consider this initial boundary layer problem. Okay, with this in these conditions here, all conditions here. So we look at the global existence of the weak solution in the sense of course the Nyon's and Ferrezos framework. So of course the related thing, of course, for lipstocks obtained by those many papers there, and MHT is some study on this similar on this problem, some similar study or other related model of MHT. For example, if we put a radiation or other terms there, there are also some studies on the global existence of weak solution. So here we did that. We did this one, and with my student we look at this problem, and we have this existence. Okay, so we have this global existence called the finite energy weak solution. Okay, of course we have this renormalized solution, some sense for this space, for the pressure or for the density here. You have this one. You need this to control the oscillation of the density. Okay. And you can also look at a large time period. So as t goes to infinity, this rho goes to a constant, and this goes to 0, and this also the equilibrium state. Okay. So this is in the sense of neons and ferrosol. So the idea to do that, of course, you add these approximation terms. Okay, the beta is not enough. This power beta is large. So this is beta and this is gamma different. Okay, this is from the pressure, but they add a bigger power here, gradient, and you have an epsilon term here. So first thing you want to look at the solution of this one, of this approximation problem. So you get an approximate solution, and then you take epsilon goes 0. This is vanishing artificial viscosity, and then you take this vanishing artificial pressure, take delta goes 0. Okay. And then of course you lots of efforts to prove how to pass the limit. Okay. One thing here is you need to look at the magnetic field. This is the original equation for H. But you use this condition, and so you rewrite this one. Actually, this becomes that. Okay, and so the equation becomes this, and you look at this one. So suppose U is given, and then you can solve this one. So you need to look at this one first. So this is given, and this operator from U for given U to H is continuous on this set. Okay. So you need to study this one first, and then you can produce the solution for the approximate problem.
So what is T there? You start with any T? What is capital T?
Oh, capital for any given T. Any given capital T, yeah, time, any given. And to pass the limit, there is one important technique here. You need to show that this is effective viscous flux. Okay, so you need to show that this one actually is convergence weakening in this space. Of course, this has been used by many people in other things. So this is one of the things you need to show, and then you get the pass the limit, get the global existence of these solutions. And we also look at the non-isotropic case. I'm not going to talk over here. Non-isotropic case with student, and also we also look at this the weak compactness of this problem. It means you have a sequence of weak solutions, right? And how about can you take a limit? Okay, you take if the limit of the sequence of weak solutions is still a weak solution. Okay, so this is called the weak compactness of this problem.
What's the answer? What's the answer?
Yes, you have the weak compactness. The limit of the sequence is still a solution.
The weak limit of sequence of solutions
is still a solution. Yeah.
You know this is not really true for the incompressible.
No, yeah, but for this compressible it is true here, because this is an important one, because usually if you do that, you have those estimates, you can construct the approximate problem, then you take a limit, then you get a solution. So this is also related to the existence problem. Of course, here I didn't say there's some special assumptions about the viscosities, okay, about the viscosity coefficients. Okay, so this is the weak solution. And now I will show you the incompressible limits of this about this MHD. So first I'm going to show you to take the zero Mach number limit. Okay, and then next I'm going to show you how to get the MHD from the hydrodynamic limit of V Maxwell Boltzmann equations. So first, you look at this zero Mach number limit. You take the scaling here. Okay, so epsilon is a Mach number. You take the scaling here, and you get this equation. So in particular, you have that. Okay, you get the coefficient of epsilon square over here, and you want to see if epsilon goes to 0. What do you get? The limiting equation. So you look at starting from this one. Of course, you have the existence, right? You have the existence of this weak solution. So the weak solution of this comparison problem as epsilon goes to 0 is the limit. Okay, is weak solution of this incompressible MHD. Of course, the existence of this incompressible MHD was obtained by many people. So I just quote aside some of them, and there's dot here. So many other papers also related this resistance of incompressible MHD in different setting. Okay. And so you get that, and you get this incompressible MHD. Okay, so this is limiting. And related, of course, the Navier-Stokes you have for this incompressible limit. Navier-Stokes not so studied on the Navier-Stokes here. And in particular, we show that this one is the rule epsilon, the density goes to a constant, for example 1. Okay, and this. Of course, what is P, what is Q is here. So this V is, for example, the velocity, and you can take the decomposition. So this is the decomposition, this is the projection. P is the projection, is probably standard projection operator. So this one converges strong to the U, and this goes to 0. Of course, so H epsilon goes to H, and in this law. And then you show that the limit is a solution, weak solution to that incompressible case. Okay. So this is basically about that. Then let me show you the hydrodynamic limit from the so this is called the Maxwell Boltzmann equation. So of course this one is also a classical model in kinetic theory. So I wanted this equation. This system looks like this system looks like is this one. So this is the Boltzmann. This is the Boltzmann equation. If Q equals 0, this is called the Beresov equation, right? Beresov Maxwell. So this, but Q here is not 0 here. So this is the Maxwell equation. It's the Maxwell one, and here is rho J divided by this one. So this is particular. The difficulty comes from this one, the Lorentz force. Okay, so the Lorentz force here causes the problem. So let's see. This Q is defined by this way. So this is just Boltzmann operator, Boltzmann condition operator. So this is standard one, nothing really special. So this is the standard Boltzmann operator. It's defined this way, right? All the positive part and the negative part of this one, they're all defined in this standard way. If you are familiar with the Boltzmann equation, this is really just the standard operator. And we have the angular cutoff assumption. Okay, so we will need this. This is also for the Boltzmann equation. This is especially for existence and so on. You need this angular cutoff. But a special example is this is the hard sphere model that satisfies this problem. From the Boltzmann equation, of course, you have these conservation laws, right? You have this one and this one. Of course, here you see mass, momentum, and energy. You have this electrical, and so Maxwell equations come in here. So you have these conservation laws. And of course, we have this H theorem, it's the, so we look at a Cauchy problem. Okay, this is a Cauchy problem. Of course, the compatibility conditions, and then you look at this. Let's check the related model. So first one is called the values of Maxwell equation Q equal to 0. I told you Q equal to 0 is called it's not Boltzmann, but it's Belousov. And then the Belousov-Poisson equation is like this. So you have this Poisson equation here. This is the Poisson equation. And also relativistic Belousov-Maxwell equations. You have that. So this is just one version. So this cosine star is cosine hat is equal to this. Okay. Yeah. So of course we have some other equations. And actually Shuhan told me he and his students also work on several related models. They also had actually his student finishing a thesis on this on Boltzmann, on Belousov, and coupled with many other equations. Okay. So this is just some of the related equations. But so let's see. When you have the Maxwell equation, you have this Lorentz force. Okay, so Lorentz force, I told you, it's causing trouble. So many things work here, but it does not work here, really. So for example, some related results, we have the global existence and weaker stability of the renormalized solutions. For example, Boltzmann equation, right? This is the classical results. Boltzmann equation is dipole ions and those. And also Belousov-Poisson Boltzmann equation, you have this Belousov-Maxwell equation. Okay. So and other things. Okay. Also for the Belousov-Maxwell Boltzmann equation, also what we know for this model, and we know that Yang Guo and also his student for Strand had some results on the existence of classical solutions. Okay, it's classical solutions near the Maxwellian. So it is a classical solution near this one. And we also have some weak stability results for this one. So because they didn't prove this weak stability. Okay, the weak stability actually is they will have weak stability for other equation, but because of this Lorentz force is open, it was open for a while. So we tried that and we proved the weak stability for the, but unfortunately the existence is still open. Okay, so the existence for the Belousov-Maxwell Boltzmann equation is still open. Okay, so but we prove the weak stability.
I don't understand. Can you explain this to me? So what do you mean weak stability?
Okay, you have a sequence of weak solutions.
Yes.
Okay, then you prove that this sequence has a convergent subsequence, and the limit is still a weak solution. Yeah.
So that proves the existence of weak solution for Belousov-Maxwell Boltzmann?
No, because we don't know how to put the approximation there. Put an approximation there so that you can get the bounds you want, to pass the limit.
How about the one alleles?
They got it. They did it. For those systems, for Boltzmann equation, Belousov-Poisson, Belousov-Maxwell, but not this Belousov-Maxwell Boltzmann.
So their renormalized solution doesn't work.
No, it doesn't work here. Otherwise, they got it. So if you really put in their paper, this is really an open problem for them. They try to, of course, they try. So you could both the existence and the weak stability open. For if we look at that paper, they always put it there as an open problem. Here we look at we solve the weak stability, but still not the global existence still open. We try to do that because we couldn't really find a good approximation to get the bounds we want, estimates we want, to pass the limit.
Your weak stability result is for classical weak solution.
No, this is the real normalized solution. Yeah, this is for real normalized solution.
And how about the data? Do you assume something about the initial data?
No, and yeah, of course, it's just the usual, just the normal things assumption for the existence of renormal assumption. So nothing special there. Nothing special for this.
But you don't let the initial data oscillate, right? It's fixed.
Right. It's fixed. Yeah.
Right.
Yeah. Okay, so here is the renormal solution, right? So just to remind you what is the renormal solution in the sense of Lyon's diploma. So this is the one, and especially this is for this F they have this condition. So this is why they call it the renormal solution, in order to control these oscillations of the density there, right? So of course this one, of course, if you here actually you choose this beta function, beta equal to this local 1 plus F is going to be enough for this problem. So we start from this renormalized solution. We look at the hydrodynamic limit. Okay. So again we look at the hydrodynamic. Of course here you need to do two scaling. One is use the small mean free path, and then another is loop frequency. I didn't write that because I don't really have time to write the details here. So in any case, after scaling, you have this epsilon. You have those epsilon here. Okay? You have those epsilon. You want to take epsilon go to 0. Okay? And try to get the hydrodynamic limit. So this is again, this Lorentz force is a problem, is the trouble here. Okay? You need to do estimates to make sure this one you can pass the limit. So this one gives you the trouble. And of course, this this incompressible limit is hydrodynamic for Boltzmann equation. Of course, not so studies on that for the Boltzmann equation. Of course, this one right for renormal solution to Boltzmann equation and so on. And this one, of course, we know that this one this is a paper which was cited many times, and also they won the Sun Award on this one. So this is a paper of, and recently they extended this one. Okay, they extended the results of this result to a general case and some other studies. So lots of studies. Of course, this is a hot topic. There are many studies on hydrodynamic limits on this Boltzmann equation. Okay, and still many papers there. So to look at this one, of course, is some key ingredients in the proof is one is you need to use the relative entropy. Okay, so Fg define this one. So log F over G here you have defined this way, and then you look at, so for our problem you define this H epsilon in this sense. Here what is M? M is this Maxwellian, okay, global Maxwellian. Of course here we look at this problem on the periodic domain in X. So this is one of the things you need to look at, and then you write the F, right? F depends on epsilon. Then this is the Maxwellian, and you write it this way. This is 1 plus epsilon G epsilon. Okay? So you want to see that as epsilon goes to 0, what is the limit of this G epsilon? So the G epsilon, and what is the equation you can get when epsilon goes to 0? So it turns out that the G epsilon here goes to this one. So this is the function, the limit of G epsilon. So you have H, U, and theta here. Okay? And so what H, U, F, theta satisfy the following system. So this system is called, is like the incompressible MHD. But you still have the electric field here. Okay? So this is, in literature, is called EMHD. Okay? EMHD. So this is the limit here, and you B is still the magnetic field. Okay, this is the formula, this equation, the standard thing. So this, and with And of course, the solution is still the weak solution in the weak sense, in the weak solution in the sense. So in gradient problem, you need to look at the relative entropy. Okay, you have to get a good estimate on that, and then the conservation defects. Of course, the conservation is not really. You have to try to see that the error should also go to 0, right? So this is one, and also you need to use the high regularity of this one to show the convergence of Lorentz force. Okay. So I'm not going to show the detail, but this is some ingredient of the proof. Okay. Okay, so this is we get the comparable limit, and using the no zero Mach number, and also this hydrodynamic limit, right? And now I'm going to show you the last part, which is about the zero magnetic resistivity here. So what is this? Actually, this is again, this is a problem, and we look at, and so you can, for example, we look at this incompressible problem first. So let me show you the again, the global existence is not there in the literature, even for this incompressible case. And then the problem is, okay, you don't know the functional space. How to identify a functional space where you can find the global existence for this problem? Okay, so it's not easy to do that. And then we get a global existence in Bessel space in this case. And this is joined with Gordon and also my student here. And so we get the incompressible case, but the compressible case is we're still working on the compressible case. So actually, one thing I mentioned, so for the compressible case, why I told you this one is harder than the viscoelasticity, because for the viscoelasticity, we use the good property of the deformation gradient F. We already get the global existence in Bessel space, but for this MHD, we still don't have it yet, because as I told you, we don't have that good corresponding property we need for H here. Okay, so we have to think about some other way to do it. Okay, so how do we start this problem? Actually, Gordon is a member of the thesis committee of my student. During the thesis overview, he suggested this problem, and my students immediately said that, okay, well, I think he said we can do the global existence for the compressible case. Okay, so but Gordon said no, we cannot do it, because nobody can do it. Nobody can do any global existence for the MHD in compressible case or incompressible case with the nu equal to 0. Okay, but my student said, okay, so I think well, I have some idea I can. And Gordon said, okay, I will bet $300. Then he changed his mind. Okay, let's do 100. So $100. So now we have this incompressible case, but not the compressible case yet. So I think he should pay my student $50. So because after this one, maybe $100 or another $50. So we look at this problem, and he said this is an interesting problem even in the compressible community. But I don't know if you. So we look at this problem. Okay, so we get this global existence in the incompressible case. Okay, so let me show you what is how to do that. Well, Bessel space. Well, actually, this is so far this Bessel space is called the critical space. This is actually this space now at this moment match the things we need for the incompressible case. Okay, for the incompressible case. For the compressible case, not yet. So Bessel space, of course, is used widely in the incompressible problems, right? You know, I just show you, give you the simple, just one page. Actually, if you want to look at the details, you need several pages to do that. But basically, we are looking at the homogeneous base of space. So you start with test function here with support here. Then with this condition, then you define use the inverse Fourier transform. You define this operator. Okay, the Q is here. Define this operator. Then you look at this Littlewood-Penny decomposition. Okay, so you use the Littlewood-Penny decomposition to do that. So you define the norm in this way. Okay, so you have these norms for it's called BS, and then how another norm is BST. So here is you use for Q bigger than 0 positive bigger or positive or negative, you define the same way. But for Q is negative and Q positive, you use two different index here. It's S and T. Here is just S for both S and T. So we need this is the base of space you need. Okay. And now so we have the global equation this one, so it says this way. So now we have we need a constant vector R. Okay? A constant vector R. But any constant vector, but not zero. Non-zero constant vector. Okay? So you can find two constants such that if the initial data is small in this sense, okay, so initial data is small in some sense. In this sense, is small, then you can find a unique solution, unique global solution. So of course the solution satisfies this estimate. So this one in this norm can be controlled by a constant here, then this is the norm of the initial data. Okay, so this space is this. So U is here, and H is here. Okay. So base of space looks kind of complicated, but it really works here for this problem. Okay, so we don't know other space which can work for this global existence for this problem. Of course, the natural thing is a classical solution, but even for a classical solution, you don't have it yet. Okay, so classical solution, the existence for this problem, we still we don't know how to do it. So to look at this problem, of course, we formulate this one. So we just H minus R, because we know in the perturbation around this constant vector, then the equation becomes this one. And then you define this operator, okay? Define this operator. Then you set this. The omega is not kind of like a vorticity, right? Kind of vorticity here, with under this operator here. So this is also R is has this one. So this one is important because if I equals 0, then you have trouble. So I cannot be 0. We need this operator because we have a good estimate on this RH. We need this one. And then you rewrite this equation into this form, and of course this is the one who asked this morning about the pressure, right, in compressive case. So you take the divergence of this equation, and then you have the plus P, and you move everything on the right side. Of course, then you use the incompressibility. Divergence U equals 0, then you can simplify the right side. For example, the T derivative will be gone, will be 0, right? So this is a way to determine the pressure here. So then when you look at after this reformulation, then you can look at this linear system. Look at this linear system. So you keep those terms here, and then the Ln are given functions. So for linear problem here, you consider U a given functions. Then so this is actually the main estimate you need. Okay? So this proof takes like 10 pages to estimate this 15 pages for this problem. So the paper is like 32 pages, but half of the paper is for this estimate. Okay, for this estimate here. So those operators need defined before, and then you do this iteration. Of course, you do this iteration. Okay. So you do this iteration, and what are those things? Those things are just defined this way. So L and those things, and then you're going to prove the convergence of this iteration. So this is this global solution is proved different way, right? The one way is that you prove the local existence, then you do a prior estimate, then extend it. But here you do iteration, so it's a different way to do it. Okay, so you do iteration, then you show the convergence of this one, then you get the global solution. So you need an estimate. For example, you need like an S-column, lemma, a theorem, and other things to prove the convergence. Okay.
So it's a fixed point theorem you use?
S-column, convergence.
That's
Yeah. So then from here you just get the global solution. Okay.
Wait a minute,
So,
it's a last colleague, I mean, then you get subsequence. But then if UN converging, UN plus 1 does not converge. I mean,
no, actually no. You get it. You get just one of the pros, right? You get it. Then you are able to.
the alternative procedure of Silas Curry cannot help you because you have subsequence converging.
Yes, then you have to do arguments. It works for everyone. Yeah.
This was the
So then for this test you can get the global solution. So we didn't try. Actually, there's some people try to use this way to do the viscoelasticity. Okay, so for the incompressible case, okay, some try to do this, but for this one, you need to do lots of estimates on this edge here, because the edge does not have a good viscous torque here. So the dissipation for edge is not there for this problem. So you need to make sure everything works for the edge here. Okay, so this will be the problem. So then we have you can get the limit, for, of course, for small data. Okay, for small data. So and then you have the global existence. At this moment, we only have the global existence in the base of space. Okay, so of course, the interesting problem was still to look at can you prove the global existence even in the classical sense, classical solutions, and we do not, or the weak solution, right? In the weak solution in the renormalized sense. So two extreme cases still open. Classical solution even with small data, a global solution, a global weak solution in the nuance sense. So two extreme cases still open. Okay. So this is, and we are working on this compressible case. So this is why. So let me show what I told you about this in MHD. So we show that the global weak solution, and we look at the incompressible limit also. One from the zero number limit, and another is hydrodynamic from this VMB, and also we look at the base of space for this zero. So this is kind of difficult. And as told you, it's people interested in the viscoelasticity, also interested in this MHD with zero mathematical coefficients, because they are very similar. Okay, so very similar. But on the other hand, this could be higher than the viscoelasticity. Okay, so if we can solve the viscoelasticity, maybe you can solve the corresponding problem. Oh no, if you solve this MHD problem, okay, maybe you can solve the corresponding problem for the viscoelasticity problem. Okay, so we are still looking at those things, and many issues are still there. So still not open problems. So.
What's an example of ionized incompressible